Good morning once again, everyone. So in the last class, we talked about the concept of pipelining in the CPU microarchitecture in order to exploit instruction level parallelism. That is to have multiple instructions being executed inside the CPU in parallel in various different stages in a staggered manner. So compared to our single cycle CPU, where everything happens inside one clock cycle, we have divided our data path into multiple segments: instruction fetch, decode and register file read, ALU, data access, data memory access, read or write, and then writing back to the register. So 5 different stages. And we aligned each stage into one clock cycle, a smaller clock cycle, and bring the instructions in a staggered manner, one after the other, in each clock cycle. So all our hardware units are utilized better compared to single cycle implementation, or even a multi-cycle implementation, which is not pipelined, right? So, and there we saw that the performance improvement that we are getting from pipelining our CPU is in terms of throughput, that is how often you can finish an instruction, compared to latency. Latency is the actual time an instruction spends inside the CPU, which is not improved by pipelining. It actually might be worsened a little, as you can see in this diagram. There may be some overheads added by pipelining, which makes the instruction spend a little bit more time inside the CPU compared to a single cycle or non-pipeline implementation. But because of the pipeline nature, the throughput increases, and that gives us a massive performance boost. So that was the idea of pipelining. And then we talked about different hazards that we have when we introduced this concept of pipelining. We saw 3 different types of hazards: structure hazards, data hazards, and control structure hazard. A structure hazard is where a required resource is busy, a piece of hardware is busy, being used by a different stage of execution, such as if you're using a single memory device for instructions as well as data, then fetching an instruction and reading data for previous instruction has to be done at the same time, and that creates a hazard. Right? That creates 2 different stages, instructions trying to use the same hardware at the same time, which is an hazard, and that is called a structure hazard. Then data hazards, where you need to wait, your CPU needs to wait because a previous instruction needs to complete its data writing or reading before a next instruction can access the same piece of data or same location, same register, same memory location, without any data corruption or reading wrong values. So that is a data hazard. We had a look at different data hazards as well. Then the last type of hazards was control hazards, where the control flow decisions depend on previous instructions results. So you cannot bring an instruction right after something like a branch. So we had a look at these different hazardous situations, and we had a look at how these hazards can be avoided as well. So for the structure hazard example, where you have to stall because only one memory is used for instructions and data, the solution is using different memories for instruction and data, or using different caches at least, while the actual memory device is the same. Then for data hazards, one of the possible solutions was forwarding. Without waiting for the data to be written back into the register file, just as the data result is ready after the ALU operation, you can forward that piece of data to the input of the ALU to be used by the next instruction. So that is the concept of forwarding. And then we had look at this load use data hazards, where the data is ready not at the end of the ALU operation, but at the end of the memory operation. So you can't forward it to the input of the ALU if the next instruction is fetched right afterwards. So you had to have a bubble or a pipeline stall in order to avoid this data load use data hazard. And then we talked about how code rescheduling or code rearrangement can be done by the assembler to avoid these load use data hazards and save the wasting of clock cycles. Then control hazards, branches, where the branch condition computation is done by the ALU and your next instruction is fetched at the right next clock cycle right afterwards. So if you wanted to avoid the stalls introduced by a branch instruction, following a branch instruction, you would need to have additional hardware at the instruction decode stage to compute the branch condition inside the decode stage before you go into the ALU stage. And even then, you have to have one bubble or one stall, because only the next instruction can be decided only after the instruction decode of the branch is done. So how do you get around this? By using techniques such as branch prediction. You predict that the branch is going to be taken or not taken based on certain reasonable assumptions, and you just fetch the next instruction right afterwards based on those decisions. And if your decision is correct, all good, nothing to worry about. You didn't lose anything. You didn't lose a clock cycle. But if your decision or prediction was wrong, you can still have the usual stall without any additional stalls introduced into the pipeline. So you didn't actually lose anything over doing this prediction. So that's what we talked about, and I gave you all some extra reading about more realistic branch predictions, dynamic branch prediction techniques, and static branch prediction techniques. And I also gave you some extra documents or topics about multiple issue CPUs, instructions, multiple instruction issue. So that is where the you fetch actually more than one instruction at the same time, and in order to support that, you need to have multiple copies of your hardware, and you need to be very clever about what instructions you are fetching. There are various different mechanisms, concepts that such multiple issues out of order executions are done, speculative execution are done. So I gave you some extra reading about this, about the concepts or the theories behind it, as well as some practical implementations that we have seen in the real history, real implementations here, real CPUs. So have a look at those and read some more on your own about those topics, because we are covering the very basic fundamental theories in the lectures, and we are getting some good practical exposure to complement our lectures. But the extra reading is necessary for you to grasp the real world ideas how these things are actually used in real world implementations. All right. So, okay. So today we are going to talk about talk a bit more about the pipeline operation and see how the MIPS pipeline that we have learned so far actually operates for the instructions that we are considering. Right. So this is the pipeline diagram that we are sort of familiar with. It's arranged into these 5 stages that we have done. So this is very similar to the single cycle, but the hardware are arranged into the pipeline stages that we have defined. So the 5 stages are instruction fetch, instruction decode and register file read, execute or address calculation, and memory access, read or write, and then writing the result back to a register. So let's quickly go over this diagram. So the first stage, instruction fetch, it starts at the program counter, right? So based on the program counter value, the updated program counter value, you need to access the instruction memory, and then the next program counter value is calculated, assuming that you're going to the next instruction. So that happens inside the instruction fetch stage. And the second stage, instruction decode, is once the instruction is read and delivered to the CPU, if you will. Then what you do there is you read the register file for the corresponding appropriate register operands. And the decoding also happens to decide the control signals for this entire data path. Mind you, the control signals are not shown here for the sake of simplicity, but the control signals are generated in this stage as well. Okay, so then if there's an immediate value which needs to be sign extended, that piece of hardware also operates inside the same stage, instruction decode and register read. When you go to the third stage, execution, the main piece of hardware is the ALU, which performs the correct operation on either 2 register operands or 1 register operand with 1 immediate sign extended immediate operand. And you need, of course, you need a multiplexer to select between these the 2 different types of operands, register or immediate. And at the same time, in parallel to this, for branches, you need to calculate the next program count address using the immediate offset provided in the instruction, sign extending and shifting it, and taking the regular PC+4 value and adding them together to generate the jump address or the branch address. And then in the memory access stage, the fourth stage, as the name implies, you do the memory access. You can read the memory for an address computed in the ALU or the execution stage. The address can be computed in the execution state by the ALU, and use that address to access the memory, either to read or write. Then the updating of the PC for branch instructions can happen after the ALU had decided the outcome of the branch instruction, that is the branch condition, whether the condition was satisfied or not. And right. So as I was telling, in the memory access stage, you access the memory, and also for branch type instructions, your branch condition calculation is ready, the result is ready, and the branch address calculated result is also ready. So those things can be used to update the program counter value. So this multiplexer here that you're seeing is also part of the memory access stage or MEM stage. The multiplexer that you're seeing here, it's part of the MEM stage. So that is something to note here. Also, I hope you noted that we have the branch target computation and the branch condition computation done here in the execution stage. So as we discussed in when we discussed the control hazards, if you want to avoid the branch the stalls introduced by having branches, then you would need to have an additional adder circuitry inside this instruction decode stage after the register reading to compute the branch condition outside the ALU in the earlier stage and move these two hardware execution, the branch target computation hardware also into the register decode, instruction decode and register reading stage, which would make that stage slower than usual. But you should be able to get the branch target computation done earlier, branch decision earlier. So we are not considering that here. We are not considering that technique to avoid the hazard here. This is the normal implementation where the ALU is used to compute the branch condition. Okay, so that is execution and memory access stages, and the write back stage, as you can see, it doesn't have a lot of hardware here, just the multiplexer, but as you know, the write back stage uses the register file again to write to the register file. So you should consider that piece of hardware for that stage as well. So this register file is again used, the same register file is again used in the write back stage to write the result. So that is what you're seeing here. The hardware is used by the write back stage as well as the instruction decode stage to write back the result. The result may be the output of the memory if you're reading, or the output of the ALU if it's computation, right? Okay, so as we discussed earlier, the right to left flow of this, if you look at, if you try to analyze the pipeline as a whole, then we know that we have all these hazards, and we are having some other type of hazards, because just imagine now the instruction has been fetched, right? And that fetched instruction is used for decoding and register file reading, while the next instruction is being fetched, and then you are decoding and reading the register file for the next instruction in the next clock cycle. So how would the control signals work in this scenario? Or how would the read values that you have read from the register file, how would they be available for the computation correctly in the execution stage? Because now we are reading another set of operands from the register file right afterwards in the same clock cycle. So you need, in order to avoid those, you can imagine a lot of structural data as well as control hazards will be introduced that we have not talked about so far, right? Because of this pipeline nature, parallel execution. So in order to get around that, we need new registers. We need to include new registers to make the pipeline smoothly work without any issues, without any additional hazards. So we need some pipeline registers. We are calling these new registers pipeline registers in between each pair of stages. So between instruction decode and instruction fetch and instruction decode, you need a pipeline stage to hold certain information. Then between the register reading and execution, you need another pipeline register to hold some set of information, to make sure that when your hardware in a particular stage moves on from one instruction to the next one, the data or control signals relevant to the previous instruction are still available for the following stages, to make sure that that is taken care of, we need to add these extra registers, one between each pair of stages. So before this instruction fetch stage, you have the write back, memory write back, and write back and instruction fetch. You see, you are not having a pipeline register, but you are still updating some state, right? So you're updating either the register file or the program counter based on what you have done so far in the previous instruction. And since only those data are required, you don't need a pipeline register between write back and the instruction fetch stage, right? So PC is a register, and register file is of course containing registers. So those are the things that are receiving any updated information after the write back stage. So you don't need to add another pipeline register for those two stages only, right? So without pipeline stages, we can't synchronize the operation of our pipeline properly. So that is something we essentially need, right? Then next thing we have to do is to have a look at the pipeline operation, how each stage actually operates and how the timing works and all that. So when trying to analyze the pipeline like that, the cycle by cycle flow of instructions, we can do this in two different ways. One is using single clock cycle pipeline diagram, where we are looking at a particular stage and the hardware used in a clock cycle. So we are looking at the stages separately. We are looking at one stage and the next stage we are looking at separately. So we separate the pipeline into the data path into stages and look at how the hardware is used in that clock cycle. That is using a single clock cycle pipeline diagram. Alternatively, we can go for multi-clock cycle diagram, where we look at the entire pipeline operation for multiple instructions at the same time. But in order to grasp the information provided in a diagram like that, you need to have a good understanding of what exactly happens inside the pipeline. So we first need to look at the single cycle diagrams, single clock cycle pipeline diagrams. Then we will look at multi-clock cycle pipeline diagrams, right? So we are going to look at load and store of instructions going through this pipeline, because the load instruction is what uses all the stages in the pipeline, and store instruction is also very similar to load, except at the very end, very last operation. So we are going to look at those two together and see how the pipeline is used, the hardware is used in the by those two instructions, right? So before we do that, let's recall what these two instructions are: load and store instructions. Then okay, so these are I-type instructions in MIPS, as we know. So the opcode, the most significant 6 bits. Then we have two register operands from bits 21 to 25, bits 16 to 20. These are register numbers, and the 16-bit immediate value, which is the address offset. So in the case of a load word instruction, the base register is RS, bits 21 to 25. That contains the base of the address. You need to add the offset into that base. And RT is the destination register, where the result is written into. In contrast, the store word operation, RT, is the source register, where you get the value from and write into the computed memory address. The memory address is computed the same way as in load word instruction. You have the base address in RS register, bits 21 to 25, that address, and you need to add the offset into the value provided in that register to get the memory location, and you are writing the value in the RT register into that location. No, you are not writing this particular value here. This is the address of the register. You go to that register, get the value there, and write that to the computed memory address. That is how the concept of the load and store instructions. Right, now let's take a detailed look at how these operations are handled inside the pipeline data path. Right, so remember, in the single cycle data path, all the operations, everything inside the CPU for a particular instruction happens within one clock cycle, from one rising edge to the next rising edge. In pipelined CPUs, only the operations of that stage happens within one clock cycle. Okay, so in the single cycle implementation, you need to make sure that all operations are completed and any result to be written into either the register file or the program counter or the memory for that matter are ready by the end of that clock cycle, by the rising edge at the end of the clock cycle. The data to be written into some element, some state is ready by the end of the clock cycle. Here, you need the results to be forwarded to the, not forwarded, results to be passed to the next pipeline stage to be ready by the end of that clock cycle, right? So note that difference carefully. So instruction fetch stage begins at the program counter. So any value to be written, updated value to be written to the program counter must have been ready by the previous rising edge, right? So by the rising edge at the start of this clock cycle, a new value to be written into the program counter is ready. Then, as soon as the clock cycle, the rising edge hits, your program counter gets updated. That update will take a small time, consume a small delay. That is the register writing delay. You need to hold the values provided to the register, the data value, for a certain hold time in order to make sure that the register captures that value and updates its state. So that is called the hold time, and that hold time is consumed by the program counter register to make sure the register is updated with the new value provided at the beginning of the clock cycle, right? So that will consume some time, and afterwards, with the up-to-date program counter value, you read the up-to-date program counter value, and the reading is also going to take some time. The value, newly updated value, to propagate outside the register, that will take some time. And once that value is taken out of the program counter register, that is connected to the instruction memory for you to read the next instruction. The address is provided to the instruction memory for you to read the next instruction. Usually it is the address following the previous instruction, unless there was a branch instruction in the pipeline. Okay, so the instruction memory reading also will take some time. You can assume the reading is done combinationally or asynchronously, not synchronized to a clock edge. So after the program counter write delay and read delay, your instruction memory read delay will happen. And after that time, after that latency, your new instruction will be available at the output of the instruction memory. And at the same time, in parallel to what the instruction memory is doing, once the PC new address in the PC is read, you can have the adder to add 4 to that PC value to prepare the next instruction's address, assuming you're going to the next instruction in sequence, not jumping to a different instruction, either forward or backward. So these two operations, pieces of hardware, work in parallel. The adder will have some combinational delay, and the instruction memory reading is done combinationally or asynchronously, and that will also have some delay. Usually, the instruction memory has the larger delay. Reading memory has the larger delay. Then, by the end of the clock cycle, your newly read instruction word from the memory should be ready to be written into the pipeline register, and your updated PC value should be ready, that is PC plus 4 value should be ready to be written into the pipeline register between instruction fetch and decode, right? So why do we need this PC plus 4 value to be written into a pipeline register? Can anyone tell me? The instruction word needs to be written into the pipeline register because the next stage needs that for the current instruction, right? When the current instruction moves to the next stage, you need the instruction encoding itself to decide what are the register addresses, what are the immediate operands and whatnot. So why do you need the PC plus 4 value to be saved in the pipeline register? Control flow. Can you maybe explain that a little bit more? You're correct. For control purposes. Can you maybe explain that a little bit more? Why would you need this PC plus 4 value? Yeah.
When branching, we need to know the PC, the exact PC value where it started.
Yes, exactly. That is correct. So if this is a branch instruction that we are talking about, we still don't know what instruction we are talking about, right? We are just fetching an instruction. We have no idea. The CPU has no idea what this instruction is. So if this happens to be a branch instruction, you would need this PC plus 4 value at this point in time available to be used by this adder in the execution stage to compute the branch target. To add the immediate offset, you need the PC plus 4 value stored. You can't go and read the PC plus 4 value at that point in time when you actually this instruction is actually in the instruction execution stage, because at that point in time you have two other instructions in the previous two stages and PC value is sure to be changed, right? So because of that, you need to save the current PC plus 4 result in the pipeline register. Now, when you're looking at the pipeline register, you can assume that either this is say a set of multiple registers, or one big register which can hold the instruction word as well as the PC plus 4 value. So this is a 32-bit instruction word as well as a 32-bit PC plus 4 value, address value, right? So a 64-bit register, if you will, right? So you can imagine it as one big register which can hold multiple values, or two separate registers. It doesn't really matter. Yes.
So don't we have to store the control signals also, because they are also getting manipulated, right?
Yes, but do we have any control signals generated for this instruction yet? We don't. Those signals are generated when the instruction moves into the next stage. But what you're asking is a very good question. After the next stage, you would have to be concerned about that as well. For now, in the instruction fetch stage, in this particular clock cycle, you don't have to worry about the control signals. So instruction memory reading, we don't have a control signal, right? Reading happens asynchronously, and this adder doesn't need a control signal. Program counter doesn't need a control signal. So those are the pieces of hardware used here. The multiplexer is actually used in the memory access stage. So the signal had already propagated through the multiplexer into the program counter by the start of this current clock cycle, right? The first thing that happens in the current clock cycle is the program counter getting updated with the value provided through this multiplexer. So within this clock cycle, within this stage, there are no control signals at play. So for now, we don't have to worry about it. Okay. So another thing here that if you're noticing, there are some shading added to the pieces of hardware used here. So the shading indicates the hardware is actually used here. Actually, this multiplexer, it's not very correct to shade it in this diagram because multiplexer is actually used, or it consumes time in the memory access stage, but the result is needed just to make sure that the value is propagated already. So you don't really need to have the multiplexer shaded here. Adder is used in this clock cycle. Instruction memory is read in this clock cycle. So we shade the right hand side to indicate the reading of this device, and in the pipeline register, we are writing to this register in this clock cycle or at the end of this clock cycle, which actually happens after the start of the next clock cycle, but still to indicate that this device, this piece of hardware is written to at this stage, after this stage, or rather at the end of this stage, we shade the left-hand side of it. So the meaning of shading the left-hand side is to say that this device will be written, whereas the shading of right-hand side indicates that this device will be read during this stage, right? So something to keep in mind as we move forward analyzing the CPU. So do you have any questions at this point about the instruction fetch stage? I'm trying to explain this as slowly and as detailed as possible because this is fundamental theory and you need to understand this properly before you go and study about multiple issue, out of order execution, branch prediction, and all that. Do you have any questions about what happens in the instruction fetch stage? Okay, I'll take that as a no. If you have questions, just you can ask. You can raise your hand and ask. So, right. At the end of this clock cycle, then we have two pieces of information ready to be written into the pipeline register. That is the 32-bit instruction word and the 32-bit PC plus 4 value corresponding to the current instruction, currently fetched instruction, right? So that PC plus 4 value is actually the address of the next instruction, but that next instruction's address relates to the current instruction, right? That's the one following the current instruction, and that address is also saved inside the pipeline register. Right, so that concludes the instruction fetch, not just for a load or store, for any instruction for that matter, right? Okay. Next, we move on to the instruction decode stage. Right, so what happens at the beginning of that clock cycle? At the rising edge of that clock cycle, the data to be written into the IFID pipeline register were ready, that is the instruction word, and the PC plus 4 value. So those two pieces of information get written into the register as soon as you hit the rising edge of the clock cycle inside this decode stage, right? So again, like we saw for the PC in the previous stage, there is a hold time, a small latency. You need to hold the values stable so the register can capture those values and update its stage. So some writing delay, a small writing delay will be consumed by this pipeline register. So now in the bigger picture, you need to keep in mind that we are pipelining this CPU to get better throughput, but in order to pipeline, we are adding these extra overheads of time. These overheads would not have been available in a multi-cycle, non-pipeline multi-cycle CPU or a single cycle CPU. But we are adding these overheads in order to get the pipelining done properly. But the pipelining itself will give us a massive throughput benefit. But the latency for the instruction to spend inside the CPU, we are increasing by adding all these overheads. Okay, right. Back to the details. So at the start of the clock cycle, your pipeline register gets updated with the instruction word and PC plus 4 value. That will consume some time. And a reading delay will be consumed to propagate that value to the rest of the hardware, right? So writing and reading delays or latencies rather of the pipeline register is consumed at the beginning of the clock cycle. Then what will happen? You need to provide certain pieces of your instruction word into these places, right? So just forget about the control for the moment. Let only look at the register file, right? So if we quickly go back to our instruction format, right? Now we have two register addresses, RS and RT, from bits 16 to 20 and 21 to 25, right? So for a load instruction, this is the register to be written to. For a store word instruction, this is a register to be read from, right? So note that difference. So one register operand is provided here. The other register operand is either provided there or provided here. Write register address or the read register to address, right? The RT should either go there or go there. So you need to connect it to both places. And whether you are going to control that or not, you are going to read both registers anyway. You're going to read both registers anyway. Only in the next stage, you should use the multiplexer to decide whether you use the second register that you read or the immediate value provided by the instruction for the ALU computation, right? So in reality, you're reading both registers anyway. You're simply connecting the wires to provide bits 21 to 25 and 16 to 20. 21 to 25 and 16 to 20 into these two address ports. And then this value 16 to 20 again into the write register address port. But the writing will not happen now. Writing will happen only after you have completed the memory read. So for now, we are only reading. So the two addresses will be provided there, regardless of whether we are reading the register, second register operand, or writing to that register. The address will be provided there. The bit bits will be connected here by default. So you're reading two registers anyway. Okay. And just like you spend some time reading the pipeline register, you had to spend some time reading the register file as well. So the moment the clock cycle starts, you spend time writing to the pipeline register, then reading the pipeline register, then after that reading the register file, right? So the time will consume to write the pipeline register, read it, and then read the register file from those two addresses. If this is a load instruction, we only need the first register operand, that is the base register value. Second one we will be discarding in the next clock cycle anyway, right? So that is the major component that consumes times in the second stage, in the load in the instruction decode and register file read stage. Register file will be consumed the major time. At the same time, in parallel to that, the first 16 bits of the instruction word are connected to this sign extender unit, where you will convert it into a 32-bit value by extending the sign bit, that is a 16-bit, in that 16-bit immediate value. So that will also consume some time, but compared to the register file reading, the sign extender doesn't consume a lot of time. So this is the sign extender device is a very simple device, consumes a small amount of time. The register file, you're doing asynchronous reading. That reading happens after the pipeline register here was written to and read, and the output will be available. By the end of the clock cycle, your two registers that you read, the values should be available here. The sign extended immediate value should be available here, and the PC plus 4 value that was in the previous pipeline register should be also available here, right? So again, a lot of information. More information than the previous pipeline stage actually, right? So something to consider here to get some more real feel about it. At the beginning of that clock cycle, what data are available at these outputs right at the beginning of this clock cycle? Can someone tell me? Can someone tell me what data are available at the two read ports of this register file right at the beginning of the clock cycle?
The instruction which is executing in the next stage.
Sorry, I didn't hear that properly. Can you speak up?
The instruction, no, the part which is executing in the next stage, in the ALU stage.
Yes, that is the register values corresponding to the previous instruction. Yes.
Yes,
so yeah, so what is available at these lines, right? We have two 32-bit lines here. What is available there? What are available there at that moment at the start of the clock cycle are the data values corresponding to the previous instruction, which is currently in the ALU stage, right? So at the beginning of the clock cycle, you have some data here which are corresponding to the previous instruction. After a certain amount of time, which composes of register writing to the pipeline, register reading from the pipeline register reading from the register file, after that delay, you will have the new data values from the two new registers available here, right? So I hope that is very clear to you. So, right, what else happens in this stage? Instruction decode. The control signals are also generated in this stage, right? You look at the opcode, that is the most significant 6 bits of the instruction, and generate the control signals. You remember those 9 bits worth of control signals? You need to generate 10 actually if you need to go for jumps as well. But those control signals are generated by a combinational circuit in parallel to this register file. And those signals will tell whether what you need to select from this multiplexer, whether you are going to write to the register file later. All those things are decided by that control unit. So that control unit also happen in parallel to the register reading here, but the time it consumes is less than the time consumed by the register file reading. Right? Register file reading is the dominating operation in this stage. Everything else that happens in parallel, the control unit and the sign extender unit, consume less time compared to register file reading. And all those 3 times happen, all those 3 operations happen in parallel after you get the instruction word from the pipeline register, right? So any questions about this stage? And as you have asked earlier, the control signals that you generate in this stage must be preserved because they will be used by later stages, right? So those control signals or control bits need to be stored in this pipeline register, in the next pipeline register, IDEX pipeline register, and used in the EX stage or the MEM stage or whatever that comes afterwards. So you need to preserve those control signals. What goes into this next pipeline register are 2 32-bit operands coming from the register file, sign extended 32-bit immediate value, and 32-bit PC plus 4 value, which was preserved from the previous stage, then control signals. 9 to 10 bits worth of control signals. So a lot of different values. So this is one big register that you have here in between the ID and EX stages. Do you have any questions to ask at this point? All right, so let's move on to the next stage. Right, so next stage is the execution. Now keep in mind that all the necessary information were ready to be written into the IDEX pipeline register at the start of the current clock cycle. All the necessary information corresponding to the current instruction should have been ready by the end of the previous clock cycle or by the start of the current clock cycle, which are the same thing, right? By that rising edge, right? Okay, so the main thing is the ALU operation. See, now we are considering the load instruction, not the store instruction, because now they are going to be a little bit different here by the way they use the pieces of hardware. Okay, so right, load operation, we have the base register RS coming as the first register read from the register file, save in the pipeline register. So the saving of the data in the pipeline register happens at the start of the clock cycle as usual, and the reading happens right afterwards. So two small delays are there, writing and reading of the pipeline register right after the rising edge of the clock cycle, right? So we are talking about after that. Then after that, the necessary lines are connected to, the corresponding lines are connected to the ALU, the 32-bit base register value, the value of the base register, right? That was read from the register file is provided to the ALU. Then the second operand to the ALU should be the immediate value, right? So if you go back to the instruction encoding, the second operand is the immediate value. So this immediate offset needs to be added to the value stored in that particular register, right? So that is the first one that we read from the register file, that, and the immediate value was sign extended and written to the pipeline register there. So that will need to go through this multiplexer, and the multiplexer will consume a little bit of time, right? A small amount of time after the reading of the pipeline register. The multiplexer will consume a small amount of time to update the new values at that set of wires there, that 32-bit line there. So the control signal to be sent to the multiplexer should have also been saved in the pipeline register by the control logic, generated by the control logic from the previous clock cycle. That should also connect here. We are not showing the control signals for the sake of simplicity yet. So that signal, control signal, should be connected here to make sure that you're taking the 1 input instead of the 0 input, right? I told you we'll be discarding the second register read because that is not used by a load instruction. That particular register is the one that we'll be writing into. We are not reading that for the load instruction. So the immediate value written into the pipeline register will be connected to the 1 input, and the control signal should select that 1 input to be forwarded to the output here. So this line will update a little bit later than that line, right? So after the writing and reading delays of the pipeline register and the combinational delay of the multiplexer, you will have the correct value at this input to the ALU. A little bit before that, you will have the other operand to the ALU available. Then after the ALU's delay, whatever the delay that the ALU takes to do the addition, and some extra delays for whatever the other multiplexes that you have inside the ALU, you will have the updated result here, right? The 0 result, we are not caring about that because this is not a branch instruction. For a load word instruction, we need the ALU result, which is the memory address that we are going to read from. And the control signals that go into the ALU should have been sent through the pipeline register. Okay, right. Then the address is now available after a set of delays: reading and writing of the pipeline register, writing and reading of the pipeline register, multiplexer, ALU operation. And ALU operation consists of adder plus whatever the other multiplexers and other combinational logic you have in there. And after all those delays, the new value is updated here in this set of lines, right? At the very beginning of the clock cycle, what you had here in this line was the ALU result corresponding to the previous clock cycle, that is the previous instruction, which is currently in the memory access stage. Now, after a set of delays, we will have the new value available here. In parallel to that, these two pieces of hardware are there: adder and shifting left of this immediate operand, which is needed by a branch instruction to compute the branch target. Those two also happen in parallel to multiplex and ALU. Shift left is a very small unit, if you remember. Only you need to do some rewiring there, so it consumes very little time. Adder consumes some time, but the dominating component here is the ALU. ALU might have a very similar adder there, but it also has some other components which add delays into the data path, like multiplexer. So ALU is a dominating component here. And at the end of the end of that clock cycle, you should have the ALU result ready to be written into the pipeline register. The 0 output, 1 bit of output, which is used by branch instruction, ready to be written into the pipeline register. The branch target, which was computed by this hardware, ready to be written to the pipeline register, which is not applicable for the for load instructions. then the second register read from the register file, which we didn't send to the ALU for a load instruction, sent to the pipeline register. That is, if this needs to be written into the memory by a store word instruction, which we will see shortly, right? So all those information and any control signals relevant to the devices in the following stages: data memory writing or this multiplexer control. All those control signals also should be forwarded from the previous pipeline stage into the next pipeline register, right? So in the case of a branch instruction, this PC plus 4 value, which we computed in the fetch stage, passed to the next pipeline registers without doing anything, will be used by this adder PC plus 4 value corresponding to the current instruction, and that will be, the result will be saved in the next pipeline register. Just make a note that by this point in time, the PC plus 4 value now will be different. It will be corresponding to some instruction that was fetched afterwards, right? So that is why we needed to save that through pipeline registers. Okay. Any questions about the execution stage? Right. Okay, so we'll move on to the next stage. Memory access. This is for a load. For a load, what we do with memory is we read from memory. We need an address to read from the memory. That address was what was computed by the ALU in the previous stage, which was then written or made available for the pipeline register to be written to. So at the start of this clock cycle, the current clock cycle, in this stage, again, you will have the writing delay into this pipeline register, then reading delay of that pipeline register for the values to appear along these lines, right? So this 0 output and the branch target are used if this was a branch instruction, and that would have been used by other multiplexers here and this multiplexer there to decide what to write into the program counter value. So we don't need to be concerned about those two particular values for the load instruction. For the load instruction, we need the address which was computed by the ALU and saved in the pipeline register, and we don't need to be concerned about write data. But note that the second register value, which was anyway read from the register file, regardless of whether this is a load or store instruction, will have propagated through the this IDEX pipeline register, being discarded here, but be propagated through that line into the EXMEM pipeline register and then sent to this write data port of the memory. So since this is a load instruction, how do we prevent this particular data be written into the memory at that address? Can anyone tell me? We have some data here, right? But we are talking about a load instruction. So how do we prevent that data being written? Write enable, exactly, very good. So the write enable control signal, which was generated in the instruction decode stage, saved in IDEX, saved in EXMEM pipeline registers, that should stop the data memory from writing that data. For the load instruction, that control signal value should be 0. So any data that was available here will not be written into the data memory. Then what will happen? You have the address made available after the writing and reading delays of the pipeline register. After a little while, after the reading delay of the data memory, it will take some time for the output to stabilize at the new values that is corresponding to the piece of data stored at the given address, right? So for the memory to stabilize for that reading and the data to be available here, it will consume some time, and that is the dominating piece of time in this particular pipeline stage. Any other multiplexers used by the branches or anything consume much smaller time compared to data memory read. And note that the ALU result, which is the address for this particular case, is connected to the next pipeline register as well. So what we are writing into the next pipeline register, what we are reading from the data memory, and the ALU result generated from the previous stage pass through the pipeline register and any relevant control signals for the next stage. Why are we forwarding this ALU result to the next pipeline stage? Can someone tell me? Why would we need that information to be passed into the next pipeline stage? Why do you think? To write back to register. Yes, exactly. So not in the case of a store word instruction, right? In the case of store word or load word, the ALU result will be the computed address, that is the base register value plus the offset, and that will be used by the data memory to read or write. In the case of a load, we read from that address. In the case of a store, we write to that address, that piece of data. But if this instruction was an R-type instruction or some other instruction where the ALU generated some arithmetic or logic or shifted result, then that result needs to be written into the register file at the final stage. So that instruction will not use the data memory in the mem access stage. It will just waste that time. But in the next clock cycle, you need to write that data into the register file. So that is why only in the case of a load or store instruction, this ALU result is a memory address and we use it to access the memory. In all other cases, the ALU result is a piece of data which might need to be written to the register file, right? Other than branch instructions, the ALU result needs to be written to the register file. That is why we forward that into the pipeline register. So at the end of that clock cycle, we need the data read from the data memory to be ready in this line, this set of lines, a 32-bit value, a 32-bit result from the ALU, which might need to be written into the register file in the case of arithmetic logic shifting type instruction. And any relevant control signals should be preserved or saved in this register file. All those values should be available at this point at the end of the clock cycle, right? So the dominating piece of equipment here is the data memory. It will consume the most time within that clock cycle. And okay, any other questions? Any questions about the memory access stage? I hope you're getting the bigger picture clearly now. So while this is happening for this particular instruction in this pipeline stage in that clock cycle, at the same clock cycle, the other stages will be operating like we discussed for the instructions that were subsequently fetched after the current instruction, right? So all of these are happening in parallel, but we are only looking at this stage for now for this particular instruction, right? So at the end of the clock cycle, at the end of the load word clock cycle, the data will be written into the pipeline register. Right after the rising edge that comes at the end of the clock cycle, during the first few moments of the next clock cycle, that data will be written, right? So we'll have a look at that. Write back stage. Okay. So we have this pipeline register, memory write back, that will be written to and read, right? First thing you will have, what will happen is writing to that register the values that were computed by the previous stage. And then after another small delay, the data will be propagated here. This will be the data read from the memory for a load instruction, if it was a load instruction. Or otherwise, it may be some other garbage value, right? If it's not a load instruction, it's some garbage value. Then the other thing that goes to the multiplexer was the ALU result that was formed. So the control signal should have been preserved in the pipeline register, right? It should have been preserved through all these pipeline registers to make sure that if this is a load instruction, the value should have been 0, because you need to use the data memory output to write to the register file, right? So otherwise, if this was an arithmetic logic shift type instruction, you need the control signal to be 1 in order to let that signal go forward from there. So based on that preserved control value, your result, data memory result, will go propagate from there. The multiplexer will induce a small delay in the data path. Okay, so that value is now ready to be written into the register file. That value needs to be available here in order to write to the register file. Then can you point out anything wrong in this diagram? There's nothing much happening at the in the write back stage other than this, right? It's a very small stage comparatively, but we have to have that stage. Can you look at this diagram carefully and find if there's anything wrong with this? In the write back operations, can you find anything wrong here? Write register is not the correct value. Exactly. Very good. Write register, that is, this particular port is not receiving the correct value. Why is that? Where are you getting the value to that write register port? That is from the IFID pipeline register, right? IFID pipeline register will have the instruction, and the write register, even though we are ignoring something here, the write register will have will be either, let us go back to the instruction decoding. The write register for a load word instruction, right? That is the address of the register to be written to, RT. And the other input that will go into the write register is for an R-type instruction. We will not have a big immediate value like that. For an R-type instruction, we will have 3 register operands, and the third one will be the destination register. So that pieces of address, the bits are also provided here through a multiplexer, right? So that multiplexer is not shown here since we are not considering R-type, but as it's shown in this particular diagram right now, we are reading the write register address from the pipeline register, which corresponds to the instruction that was fetched in the previous clock cycle. Whereas this load instruction was fetched 4 clock cycles ago, right? So the value, the address of the register to be written to is now incorrect. So that is a major error that we see here. The data to be written is correct, that is right. The place to be written to is now incorrect, wrong register number. We are providing the wrong register number to the right register address port here. So How do we solve that? Can you tell me how to solve that? Any idea how we solve this issue? Using a multiplexer. How do we use a multiplexer to solve this issue? Can you explain a little bit more? Chamit says store that value in a pipeline register. I think that what you're thinking about using a multiplexer is okay, it's correct, but without storing the pipeline, without storing the value in the pipeline register, that using a multiplexer, just using a multiplexer will not work. So we will have to store the value in a pipeline register. That is correct. So what we will have to do is this. Instead of connecting this set of wires from the instruction word from the pipeline register into that port, we disconnect that and we send that value to the pipeline register. We send the write register address, the register number, to the IDEX pipeline register, from there to the EXMEM pipeline register, from there to MEM write back pipeline register, and from there to the write register port. So that writing register address will be sent through the pipeline along with the instruction, the rest of the instruction operations, and made available at the write back stage. That is the correct way of doing it. You can have a multiplexer if you want, but you don't need because the writing happens only at the write back stage. Writing does not happen at the instruction decode stage. So there is no need to have another connection from the pipeline register, IFID pipeline register, to the write port here and add a multiplexer also. It's not needed. You can do it like that, but it's not needed because the writing only happens in the write back stage. So all you need to do is disconnect that previous line we had there and add a new line to new set of lines to propagate that write address through the pipeline registers and use that in the write back stage, only in the write back stage. So at the end of the clock cycle at the write back stage, the data will be available here, right? At the end of the clock cycle in the write back stage, the data will be available here. And at the beginning of that clock cycle, the register file will write that data into the data will be available here and the address will be available here, sorry. And at the beginning of the clock cycle in the ID stage, that piece of data will be written to that register number if the write enable signal was set, right? So that is one of the first things happening in that stage, which we didn't discuss earlier. So in that, not in that stage, actually it happens in the write back stage or at the end of the write back stage, but it will coincide with the instruction decode of a subsequent instruction, right? The writing will happen, but at the same time, some asynchronous reading will happen for a later instruction. So will that create any issue? Writing of the register takes a small time. You need to hold the data and address table for a little bit of time for the register to capture that value. And from the same rising edge, your instruction, some later instruction, which was stored in a pipeline register here, will be written to the pipeline register, then read, and the reading will stabilize here. So the reading will stabilize with, if you are reading the same register that some previous instruction is just now writing to, that will not create an issue, because during at the end of the clock cycle, the read data will have stabilized, and because you spend some time here for the instruction to decode, and the writing will happen in parallel to the register writing of the pipeline register. So by the time the address propagates here, you have already updated the writing register. And at the end of the clock cycle anyway, these values would have stabilized at the new up-to-date value if you are reading the same register that was written to in this very stage at the same time. So you would need to consider the same concept you would have considered, I think, when you were making the register file for your CPU, for our ISA. When you were making the register file, you would have had the same similar problems where you need to synchronize, you need to pay attention to the timing. Okay, any questions? I took a long time to explain all this because it's necessary for you to properly understand how the pipeline operates perfectly, right? So this is a very simple example. In order for you to understand all the other advanced concepts related to this, you need to understand the basic theory very thoroughly. Okay, so let's move forward. So that is the end of the load instruction. For the store instruction, in the execution stage, the address computation is the same, right? You get the base address from the pipeline register. You get the immediate value from the pipeline register. And the correct control signal should be provided to the multiplexer to read the immediate value and add them to generate the address through the ALU to generate the address that should be later sent to the data memory to write to. Then the data to be written to is coming from this second register that we read, and that is directly supplied to the pipeline register through that line, right? So the pipeline register at the end of the execution clock cycle, at the beginning of the memory clock cycle, it will update with the new values, and the address will be provided to the memory, the write data will be provided to the memory, and the write control signal should also be provided through these pipeline registers into the memory. So this piece of data will be written to that address, and that is what the store word instruction does in the memory access stage. And the value that you're reading here is not relevant. We are not going to use that in the write back stage. And actually the store word instruction, it does nothing in this write back stage. Its writing was done to the memory in the memory access stage. The write back stage deals with register writes. So you're not writing anything to the registers from a store word instruction. So that's the difference. Right. Okay. So that was using single clock cycle pipeline diagram. Now let's have a quick look at a multi clock cycle pipeline diagram where we see the operations of multiple instructions in parallel at the same time, right? So if you just cut a section across these different data path operations for different instructions, you can see what happens in parallel in the same clock cycle. In say clock cycle 5, a lot of different things happen in parallel in these 5 stages for 5 different instructions, right? So just as I told you before, the shading of the right hand and left hand side indicates whether you are reading or writing. Right hand side meaning reading instruction memory here, reading register file here. This is writing registers, right? So, okay. Again, can you find anything wrong in this diagram? Have a careful look at it. Have a look at the instructions and what they are doing at each pipeline stage, and tell me if there is anything wrong here. For example, this instruction, load word base register, immediate offset, destination register, right? In the fetch stage, you read the instruction memory, you have the pipeline, you go through the pipeline register. In the next stage, you read the register file, go through a pipeline register. ALU computes the address, go through a pipeline register. Data memory is read, go through a pipeline register. The value you read from the data memory is written to the register file, right? So that is what happens in that data path over the pipeline stages for load word instruction. Like that, when you fill the pipeline gradually, is there anything wrong? Can you find anything wrong in this diagram? Third instruction uses wrong $3 value. Can you explain that a little bit? What do you mean by wrong $3 value? I think you have found the error. Can you explain that a little bit more? $3 register value is not updated. You mean a pipeline hazard? Okay, it's not updated yet, right? Yeah, fair enough. So you need to have, since you generate the result. Wait. Actually, no. This is not a result, right? $3. This is an operand register. This is not not the destination register. Destination register is $11, right? So you're writing to $11, and you're not reading $11 right afterwards here in that instruction. So actually, there is no data hazard between this sub and add. I can see that how you can mistake the destination register, but if you recall the format of the textual assembly instructions, sub, destination register, and the two operand registers, two source registers, that is the order. So 11 is the destination. Can you find anything else wrong in this diagram? I'll give you a hint. So the sub instruction, coming. Add uses data memory, exactly. So this add, the diagram says add uses data memory. Add reads from data memory, which is wrong. Add doesn't use the data memory. Add reads only register file and then writes the register file. So this is wrong. Whereas this load word instruction, the diagram says it's not using data memory, which is wrong. Load word reads from the data memory and writes the register file. So there is an error here. Actually, this error is in the book as well. So I took the diagram from the book. So when you're reading the book, something to keep in mind, this is not correct in this diagram. If you come across this diagram in the book, when you go and read more about pipelining, this is one error present in the book. So keep that in mind, right? Okay, good. So this is the traditional form of a multi clock cycle pipeline diagram, which we have used earlier as well when we learned about the pipeline concept. So there, you don't really show the resource usage. You just say what happens at each stage, only the operation, not what resources are used. So clock cycle 1, fetch, clock cycle 2, decode, 3, execution, 4, data access or memory access, and 5, write back. And the same is staggered for the subsequent instruction, but the this form of the diagram shows more information, contains more information. It shows what resources are used and how by each instruction at each stage. Right? So it's a more informative diagram, but pay attention to little errors like that. Okay, so right, so let's summarize what we have discussed about pipelining so far. The concept of pipelining was introduced to improve the performance by increasing the instruction throughput. How many instructions can you complete per unit time, right? So it's, keep in mind that it's different to the latency of the instruction. Latency is the absolute time the instruction consumes inside the CPU. That is not what we are improving by pipelining. Throughput is what we are improving by pipelining. Actually, we are increasing the latency, but the actual effective throughput is improved, right? So how do we do that? By executing multiple instructions in parallel. By using the different hardware maximally in parallel, you can have a staggered setup where different instructions are being served by different pieces of hardware at the same time. Then the latency for each instruction, we are making it the same. Remember, after the single cycle implementation, we said the latency is still the same for all instructions, but not all instructions use all hardware. So a non-pipeline multi-cycle implementation of the CPU improves the latency for instructions by making some instructions spend less time in the CPU by using only the necessary pieces of hardware, right? But with pipelining, we again make the instructions latency same for all instructions. Compared to single cycle, that latency is increased because we add certain overheads to have the pipelining functionality. But since we exploit the parallel execution, instruction level parallelism, we get better throughput, resulting in better performance, right? But as I said in the previous lecture, it's not all rainbows and unicorns. It's there are some issues with pipelining hazards where we categorize them as structure, data, and control hazards, where we may not be able to keep the pipeline in the perfect steady stage because of dependencies between instructions, dependencies between pieces of hardware, dependencies between data, or control decisions, right? So because of that, we need to stall the pipeline. We need to install bubbles. So that is unproductive work we do with the hardware, right? We let the hardware idle for certain clock cycles, certain hardware are idle. So that was to avoid hazard. And then we came up with some solutions to avoid these hazards as well, to keep the pipeline benefit, throughput improvement, or speed up to maximum possible without having to introduce stalls into the pipeline unless absolutely necessary, right? So there are solutions to almost all kinds of hazards available that we discussed, right? And then one other thing to keep in mind is the instruction set itself, the ISA, affects the complexity of the pipeline implementation. And like I told you, like we discussed, the MIPS ISA was designed to be implemented as a pipeline, not as a single cycle or a non-pipeline multi-cycle implementation. MIPS was designed to be implemented as a pipeline, and certain characteristics of the ISA supports that, like the func field being separated and all that, right? So it has the instruction set was designed keeping in mind that this will be implemented as a pipelined version, right? And in the MIPS pipeline, we had 5 stages, and if you do a little search of your own, you can find pipelines which contains so many stages. If I can't remember the names right now, but this when the first concept of these netbooks appeared few years ago, right? The little cheap computers to be used for web browsing. Those I think Intel Atom was one of the processors introduced to be used in those that type of devices. Cheap, power efficient, and I think those had one of the longest pipelines in the history. Some 30 odd stages in the pipeline, right? A massive number, but obviously those didn't perform amazingly well. You don't get a throughput increment as much as that because there is a limit you can exploit the instruction level parallelism. You cannot go and keep a steady pipeline running with that many stages. You will have to flush the pipeline, you'll have to stall a lot. So your benefit is not really 30 something times compared to a single cycle, or 4 or 5 times compared to a say 6-stage pipeline or something, right? So have a read about that. Just go into Google, type these things, and read about different real pipeline implementations in real processes. You'll find some fascinating information, and since now you have a good idea about the fundamentals, you'll be able to understand most of the concepts there and read about those extra topics that I gave you: multiple instruction issue and out of order execution and things like that, speculative execution. All those are advanced concepts used in real CPUs. So read about those as well. Right. So I will upload these slides into Moodle, and there are a set of exercises for you to go through and solve. So you might have to make some assumptions for some questions, some exercises. So what you can do is post your answers in the discussions forum. There was some issue not being able to reply in the discussion forum, so I think I have fixed that. Now you can reply. Post your answers there and discuss, help others out as well. I will also try to help you there. So I'll just quickly go through a couple of exercises to help you out. So in this first exercise, it says the table given below states the latencies of hardware components of a 5-stage pipeline MIPS data path, right? So something similar to what we have discussed. Assume memory write latencies are smaller than corresponding reading latencies. So instruction memory, you don't write to, you only read, so that doesn't apply. Data memory, reading is 250 picoseconds delay, latency rather, and the writing of data memory has a smaller latency compared to this reading of data memory, right? So the number is smaller than 250, right? That's the assumption. So the first question is calculate the maximum clock frequency of the processor. Can we try to do that quickly? So we have all the information here. Here is a pipeline diagram to help you out. 5-stage MIPS pipeline. So to decide, the question is calculate the maximum clock frequency, right? That is, we need the clock cycle, which should be same for all stages, right? And the clock cycle is decided by the slowest stage, the stage that consumes most time, and the smallest clock cycle, such clock cycle that you can use is the maximum clock frequency that you can get for the CPU, right? So can you try and compute the times for each stage and tell me the maximum clock frequency you can use, or the maximum minimum clock period that you can use rather? So in the instruction fetch stage, you start with the PC. You have to write to that register. It's a register write, right? The 30 picoseconds. And then you have to read that register to access the instruction memory. Register reading is 90 picoseconds according to this. So you spent 120 picoseconds just on the program counter. And then instruction memory reading takes 200, while at the same time the adder is spending 70 picoseconds. So this is the dominant device there, the instruction memory, and it spends 200. So 200 plus 120, 320 picoseconds you spend in that clock cycle, right? To make sure the data is available in those lines. 320, right? So if you want, we can put a little note here. So this stage 320. Can you tell me the number for the instruction decode stage? Remember that at the clock cycle, you start by writing to the pipeline register. Writing 30, then reading the same register 90, 120. Afterwards, you need to figure out the largest delay in that section. Can you quickly tell me what is the number for the ID stage? What is the number for the instruction decode stage? Can anyone tell me? 210. So you spend 120 on the pipeline register, writing and reading, 120 picoseconds, and then the register reading delay is 90, so 210, right? So 210 picoseconds, that is correct. What about the instruction execution? Execution stage? What's the time? 120 for the pipeline register operation, and from there onwards 230. And what does that include? So the shift left operation 10 picoseconds and adder 70, so 80 altogether for that. In parallel to that, the multiplexer 20 and ALU 90, so 110 added with 120, that is the dominant delay, so 230, right? So 230 picoseconds there in that stage, right? Then the data memory access stage, 120 for the pipeline register, then 250 for the data memory, that which makes it 370. That is correct. So 370 picoseconds is what we have there, right? So 370 picoseconds, right? So what about the write back stage? Write back stage 170, that is 120 here, multiplexer 20 and register writing 30, right? So 170. So multiplex is 20 and register writing 30, so that is 50, 170. So this stage 170 picoseconds you are spending, right? Correct, very good, right? So based on that, what is the clock period of our CPU that we should use? The minimum clock period that we can use? 370, right? It is dependent on the largest delay of the data path, any largest delay at any stage, because each stage should use the same clock cycle, same clock period. So the clock period we have to use is this 370 picoseconds, and the maximum clock frequency is equal to 1 over 370 picoseconds, which will give you some hertz number, right? Some megahertz or gigahertz number, you can calculate that. So that will be the maximum clock period, maximum clock frequency you can use in this CPU. So the next is you have to suggest a mechanism by which we could increase the clock frequency of the processor. Then any negative impacts of performance by that technique you suggest. So in order to increase the clock frequency, now our clock frequency is dependent on that, that is the bottleneck. And if we want to increase the clock frequency, you have to improve that stage, right? So what you can do to improve data memory access time and register access time, register reading and writing time, which is a very small time compared to what the data memory is consuming. So that is the dominant part. So how do you improve data memory access time is what you have to look into to answer that question, right? So quickly, they'll be disturbing us in the next slides, right? So have a look at that exercise and these other exercises as well. I will upload them after the lecture. And okay, let's quickly look at this exercise. Exercise 6 is the last one. Yeah. So, okay. Part A, consider pipeline process architecture. Assume that the time taken to execute an ALU operation can be shortened by 25%, right? So you have a pipeline process architecture which has an ALU stage, and the time taken to execute this ALU, inside the ALU, the operation can be shortened by 25%, right? So you see that there can be some optimization done to the ALU, which will shorten the time by 25% for that particular stage. Will it affect the speed up obtained from pipelining? What can you say? If yes, by how much? Otherwise, why? Why can it not? What do you think? Will it affect the speed up obtained by pipelining? Speed up, remember, it is referring to the throughput. Will it affect the speed up obtained by pipelining? What do you think? Shortening the ALU period. What can you say about that particular question?
If ALU time taken is the most out of the others, yes.
Right. Yeah, exactly. That is correct. So if it's the slower stage, if the slower stage contains the ALU operation, then the throughput will improve. That is correct. If we assume that this is staged like the MIPS pipeline, where the ALU has its own stage and the critical stage is the memory access stage, as we saw before, then in a usual or more typical scenario like that, the data memory access stage dominates the timing. So in a typical scenario, improving the ALU will not get you better performance. So that is the concept of the answer. So you can build your answer based on that. So there are a lot of ifs and buts here. So you should be able to arrange the argument saying if this is the case, this is so, otherwise this is, and why, and all that you can provide for the answer. Let's have a quick look at the next part B as well before we wrap up. A computer architect needs to design the pipeline of a new microprocessor. She has an example workload program, right? She has an example sequence of instructions with 10 million instructions, right? 10 to the power 6 instructions. A program with 10 to the power 6 instructions. Each instruction takes 100 picoseconds to finish. Okay. So 10 million instructions with 100 picoseconds per instruction to finish. That is the latency, right? Each instruction takes 100 picoseconds to finish. So first question is, how long does it take to execute this program code on a non-pipeline processor? In a non-pipeline processor, that is, it could be a multi-cycle non-pipeline or a single cycle processor. Either way, we have been told that each instruction is taking 100 picoseconds, the same latency for every instruction. So it's probably more like a single cycle CPU, right? So how long does it take to execute this program? Right, 0.1 second, right? That is 10 million times this 100 picoseconds. So you have to spend that much time, 100 picoseconds per each instruction for this 10 million instructions. So yeah, that is correct. Then the second question is, the current state of the art microprocessor, the latest microprocessor, has about 20 pipeline stages. Okay, the data path is divided into 20 pipeline stages. Assume it is perfectly pipeline. Perfectly pipeline meaning we have divided the workload perfectly evenly, right? We saw in the MIPS architecture that we just looked at, there's a lot of disparity, right, between the stages. But assume that this 20 pipeline CPU is a perfect pipeline. Each stage has the exact same workload and there are no overheads added. How much speed up will it achieve compared to the non-pipeline processor? Compared to the processor in this part I, or part 1 rather, part 2, how much of a speed up throughput increase you will be able to get by this 20 stage perfect pipeline? How many times? 20 times, yes, exactly. 20 times. 20 times speed up can be gained by a perfect, ideal pipeline, right? So part 3, real pipelining is not perfect, as we have seen, right? Since implementing pipeline introduces some overheads per pipeline stage and the workload is not evenly distributed. Will this overhead affect the instruction latency or the instruction throughput, or both? What do you think? All right, I don't need an answer, direct answer right now. That is something for you to think about and work out. So since it's already 11, we'll have to pass 11 a little bit. So we'll stop. And yeah, so go through these exercises, read all the extra reading that I have given you, and do some searching on your own to find out what is out there in real pipeline implementation CPU, right? So you, I think you have gained a lot of knowledge at this stage. So from next week onwards, we'll be talking about memory. So far, we've been talking about the instruction set architecture and then the CPU microarchitecture. Now, the next big thing we are going to talk about is the memory subsystem. How do you store and improve performance in memory, because memory is usually the performance bottleneck in nearly all CPU implementations. So that is what we will be talking about from next week onwards. So yeah, so this is it for the pipelining topic. I'll stop the recording now.